The greatest common divisor is another grade school concept that turns out to be incredibly powerful and useful in the world of encryption. All of these bits and pieces that we're forming are soon going to come together in the form of this RSA encryption algorithm. But before we do that, let's go ahead and revisit what greatest common divisor means. So let A and B be integers, not both 0, otherwise it's a fairly boring process. The largest integer d, such that d divides A and d divides B, is called the greatest common divisor of A and B. So it's a divisor that A and B share in common, but it's the largest such divisor that A and B share in common. And we often will write GCD parentheses A comma B to indicate that that's what we're going to output. So the GCD is sort of a function, if you will, that takes in two values and outputs 1. So if we look at the GCD between two numbers, say 4 and 8. Well, first of all, we see that 4 and 8 both have divisors of 2. And that leaves us with 2 times 2 for 4 and 2 times 4 for 8. So 2 is indeed a common divisor. However, it's not the biggest common divisor. We can see that 4 and 8 can actually both be divided by 4, and that is the greatest common divisor. After all, 1 and 2 are no longer divisible by any common value. So we would say that the GCD between 4 and 8 is 4. Now we can also look at larger numbers, the GCD between, say, 26 and 32. Okay, so I can think about some of the factors of 26 and 32. 26 has factors of course, 26 in itself. 32 has factors of 32 in itself. But I could actually divide 26 by 2, and that leaves me with 13. Now 13 is a prime number. That's not divisible by anything other than 1 in itself. But 32, if I look at 32, 32 is also divisible by 2 and leaves me with factors of 2 and 16. Now 13 and 16 no longer share a common factor, and so the GCD between 26 and 32 is 2. That's the largest number that divides both of them. Soon we'll establish how we locate such a greatest common divisor in a more algorithmic way. One important definition that we need is this definition of two numbers that are relatively prime. So the integers A and B are called relatively prime, meaning neither one has to be prime in and of itself, but we're going to say they're prime relative to one another if their greatest common divisor is 1. So for example, if I look at the GCD between 5 and 12, well, 5 has factors of 5 and 1, 12 has factors of 2 and 6, 12 and 1, 3 and 4, but the only number that divides both of them is, in fact, 1. So we would say that 5 and 12 are relatively prime. Another example of that could be where both the numbers are prime, like 5 and 7 are considered relatively prime. In fact, 5 and 7 are both prime. And there are cases where neither of the values is prime. So the GCD between, say, 15 is not prime, and 22, well, the factors of 15 are 3 and 5, or 15 and 1. The factors of 22 are 2 and 11, or 22 and 1. And therefore, the only factor that divides both of them is 1. So 15 and 22, neither of which is prime, are considered relatively prime. So we have relative prime here, we have relative prime here, and we have relatively prime numbers here. All right, that's going to become an important definition, as part of the RSA encryption algorithm requires us to find values that are relatively prime. Now here's an important lemma, or really the result of some theorem or some kind of important in and of itself type of theorem that is derived from another theorem. So let A equal BQ plus R, where A, B, Q, and R are integers. Then the GCD between A and B, in other words, the GCD between these two numbers, is equal to the GCD between these two numbers. So let's see what we mean here. Let's pick A to be the larger value, and A, let's say that that number is, we'll say 15, and we'll say that B is the number 3. Okay, so if I write this expression, A equals B times Q plus R, now typically we think about Q and R as the quotient and the remainder. So what I'm really asking for here is 15 can be expressed as how many multiples of 3? Well, 3 goes into 15 exactly 5 times and leaves a remainder of 0. And we're saying that the greatest common divisor between these two numbers, A and B, which is the GCD is 3, is the same as the greatest common divisor between 3 and 0. Well, the biggest number that divides 3 is 3, and 0 is divisible by anything, and therefore we can say that the GCD between any number and 0 is that any number. So the GCD here is also 3. I can look at another example where maybe we list A equals 26 and B equals, we'll go with 28, and we'll go with B equals, we'll say, let's pick another number. Let's pick 35 and 2. So 35 can be expressed as 17 multiples of 2. That gives me 34, but it gives me a remainder of 1. If I look at the A and B values and think about what their GCD is, well, 35 is not divisible by 2, and 2 is only divisible by 2 in itself, so the GCD between these two numbers is 1. Then if I compare the B value to the remainder, the GCD between 2 and 1 is definitely 1. It's the biggest number that divides both of them. And so here are just examples of why this lemma works. But this establishes something incredibly important, which is often referred to as the Euclidean algorithm, named after Euclid, which allows us to find GCDs by sort of exploiting this lemma. So this lemma allows, because it relates A and B to B and R, it allows me to construct a series of equivalent statements which ultimately leads me to the GCD between those two numbers. So back up here, we saw that the GCD between 4 and 8 is 4, and between 26 and 32 is 2. So let's focus on 26 and 32. So I'm going to pick A to be the bigger of the two numbers, and B to be the smaller of the two numbers, because that's typically how we're going to use this lemma. And so what I'm going to start off doing is expressing A as a certain number of multiples of B plus the remainder. So in this case, A is 32, B is 26. And so what I'm asking is how many times does 26 go into 32? Well, it goes into it once, and so my quotient is 1. But that leaves a remainder of 6. And so what I know now is that the GCD between 32 and 26 is the same as the GCD between 26 and 6. So what I'm going to focus on is I'm going to kind of shift these two values over, and I'm now going to focus on the relationship between 26 and 6. So I'm going to ask, how many times does 6 go into 26? Well, it goes into it 4 times, leaves me with a remainder of 2. 6 times 24 is 24. 26 minus 24 is 2. And now what I can say is that the GCD between 26 and 6 is the same as the GCD between 6 and 2. Why can I say that? Well, because this expression, or this equation here, is exactly A equals BQ plus R. And we know that the GCD between A and B is always going to be the same as the GCD between B and the remainder. So what I'm doing here is I'm basically reducing these numbers in size each time. So now I'm going to focus on 6 and 2, and I'm going to say 6 is equal to how many multiples of 2? Well, 2 goes into 6 3 times and leaves me with a remainder of 0. Now if I stop here and I look at the equivalent statements, we've basically said that the GCD between 32 and 26 is equal to the GCD between 26 and 6, which is equal to, well, because 26 and 6 have the same GCD as 6 and 2, so I can say that this is the same as the GCD between 6 and 2. And notice that the sizes of these numbers, a and b, is getting smaller and smaller. And now in my final statement here, now I'll go ahead and look at these two values. The GCD between 6 and 2 is going to be the same as the GCD between 2 and 0. And now I can stop, because once one of my values, a or b, is 0, then the GCD between a non-zero number and the 0 number is going to be the non-zero number. So 2 definitely goes into 0, 2 goes into 2, 2 goes into 6, 2 goes into 26, 2 goes into 32, and so from my previous step, right here, after I get that remainder of 0, my remainder from the previous step is in fact my greatest common divisor. And all of these equivalent statements lead to that same conclusion. Once you get to a point where your remainder is 0, then your GCD for the original two numbers is the remainder from the step previous to it. And this is a very nice algorithmic way. You can see that it converged in really 3 sets of computations. So we were able to find the GCD very quickly. One way you might hunt for the GCD is, without knowing this algorithm, is to just start dividing these numbers by something. So does 2 divide it? Okay, so if 2 divides it, and I divide both of these by 2, then I get 16 and 13. And then I kind of keep trying to repeat this to see if there's additional divisors. And then I could actually multiply all of those divisors together to find the GCD. But since divided by, I can only divide these by 1, and those numbers no longer change, this number times this number, well, that's the product of my 2 divisors, that's going to be the GCD. But you can imagine for large numbers, this would be a very painful process if you weren't using the Euclidean algorithm. It turns out that we can do this for really large numbers too. Let's say we want to find the GCD between 296 and 124. So I'm going to start off the same way. I'm going to write this in the form A equals Q times, or B times Q plus R. And I'm going to pick the larger of the 2 numbers, because again, that's usually the way this works nicely. 296 equals how many multiples of 124? Well, I can do the calculation. I could take 296 divided by 124 in my calculator. I'll go ahead and do that, which comes out to 2 point something. 296 divided by 124 comes out to 2.4, which means that 124 goes into 296 2 whole times, and then I can do 296 minus 124 times 2 to give me the remainder, and that gives me a remainder of 48. So now the GCD between A and B is the same as the GCD between B and R, so I'll copy those down to the next line, and now focus on 124 and 48. So this number only goes in twice, forms 96, and that leaves me with a remainder of 28. So I'm going to repeat this process again, and the GCD between 124 and 48 is the same as the GCD between the 48 and 28. So now I'm going to focus on 48 and 28. And 28 goes into 48 one time, leaving me with a remainder of 20. Once again, the GCD between A and B is the same as the GCD between B and R. So I will take those 2 values and focus on them. Again, notice how much smaller these are getting as we go. 20 goes into 28 one time, leaves a remainder of 8. So this particular set of values requires a little more computation before the process converges, but nonetheless, we're getting closer. The GCD between 28 and 20 is the same as the GCD between 20 and 8, so I'm going to focus on the GCD between 20 and 8. 8 goes into 20 2 times leaves a remainder of 4. The GCD between 20 and 8 is the same as that between 8 and 4. So now I'll focus on 8 and 4. 4 goes into 8 2 times, leaving me with a remainder of 0. And hey, guess what? Because the GCD between 296 and 124 is the same as 124 and 48, is the same as 48 and 28, is the same as 28 and 20, is the same GCD, and so on, this value right here represents my greatest common divisor. So my greatest common divisor is 4. And this algorithm sometimes takes a little bit more time for it to converge, but it still only took 1, 2, 3, 4, 5, 6 sets of computations.